Wait, I think only three joined, huh? From the class. I think still some more to join, right? So another 5 more to join. Total 11, right?
Yes, sir.
Okay, so before, do you have any, first of all, do you have any questions from the last classes or so far? Are you able to follow everything?
Sir.
Yeah. Yeah, who is there?
Sir,
Ah.
I don't have any doubt actually.
Fine. See, I want to give 4 assignments for each group. Let us say you are 11, right? In that, at least, the 3 things. One is polar coordinate, cylindrical coordinate system. Okay. 2-dimensional polar coordinates and 3-dimensional cylindrical coordinate system, spherical coordinate system. These 3, at least polar coordinates, whatever is possible, all the equations I want you to write in the whatever so far. Okay, so all the equations, whatever we derive, I want it in the polar coordinate system. And polar and cylindrical, anyway, see, almost similar. That I think a few people can take. 3 people, okay. And then spherical coordinate system, another 3. Okay.
Yes, sir.
There is something called proof of Helmholtz theorem. So I'll explain. I think today once the class is finishing. So that will be another lesson. Or the third one you can take up another. Or you see 3 plus 3 6. Another 5 are there, right? Another 3 can take up that other that's torrential or something we gave some system. So on that you can derive. All the 3 I want you submit the assignment, so that at least we assign some marks for that.
Sir, can you please repeat it once again?
Cylindrical coordinate system, three people. First, who wants to do polar and cylindrical coordinate system? All the equations, whatever you have defined so far, gradient, divergence, curl, and finally the equations of motion. So far, whatever the governing equations, I want you to represent in polar and cylindrical coordinate system. I remove that. That is your polar coordinate. Okay, so that is for three people. I want you to do three of them. Similarly, spherical coordinate system equations, all those operators and equations, governing equations in spherical coordinate system. Another three. Remaining five are there. No, total 11, right? So another three. We said something. No, some one of the lectures torrential coordinate system, some special coordinate system. No, you give any one of them, right? So that's what I gave, right? Did I give you? They give you that special coordinate system that we talked, right, sometime back. While I was teaching that one. Or did I write it inside? Video. Toroidal coordinate system we wrote now in lecture 7.
Yes, sir.
Yeah, that you can take up. Okay, so one of them for that. So you have polar and cylindrical one. The last page of lecture 7, if you see, polar coordinates 1 and 2, the cylindrical and polar coordinates, three people can just do, okay, as assignment. Spherical, another three people. Toroidal coordinate system, another three people. You do that, okay? That is one. And remaining two, I want to give them something like Helmholtz theorem. So Helmholtz theorem proof you can find out and easily you can derive it. Okay. So it tells you that divergence, suppose it is equal to 0 for incompressible flows, then that u vector, that velocity vector, you can give some curl of some vector field. Okay. So del cross some vector.
Excuse me, sir.
Yeah.
When will we have to submit it?
You can do it now. You can start doing. So next week you can do.
Okay, sir.
Okay, so that Helmholtz theorem, basically what you do is any vector field, you have its rotational component and irrotational component. Irrotational component will give you basically gradient of a scalar function. So Helmholtz theorem basically tells you that any vector field can be decomposed as gradient of some scalar function plus some del cross some vector field. So basically curl of some vector field. Okay, so that's what usually you do. That if you just check it on the web, you can find out proof. So you can neatly you can write and keep it. If you don't understand, come to me. So remaining two. So I want you to first make those groups three, three, three. First three, maybe that's better. First three, next three, next three. So we have first three. Okay, 9 are there. Remaining two, 10 and 11. Whoever in that list. Okay, so you have the list now. List of students or by we just give by go by numbers 1 2 3 roll numbers 1 2 3 cylindrical coordinate system and polar. Okay, 4 5 6 spherical, 7 8 9 toroidal, and then 10 11 uh, you can take up this Helmholtz theorem. Okay. So all are now present now, right now. All are joined. Still, I think. Oh my God! So still five more people to join. What happened to them? Do they not know that I'm taking it 6:30?
Sir, we think they are in the bus from the college. That's why they are unable to join due to network issues.
Oh, they'll have to go home and join, is it?
Yes, sir. It's like in the bus there is no network connectivity, maybe.
No, no. Bus means where they are going.
They are coming from the college to hostel, sir.
Oh, on the way. So they may join anytime. You mean?
Yes, sir. I will call them once again to
Uh,
verify it.
just check out. Okay. So, can do little bit. 7 join. Already 6:45. So shall I start then?
Yes, sir.
Yep.
We can.
Okay. So suppose see we actually gave the definition of incompressible fluid. Okay. So if let the fluid be incompressible. I think they'll be able to follow. Okay. So a fluid be incompressible. So what is that first definition that we gave? Is basically that volume, no WT. So volume of WT. Volume of WT is actually constant, right? So that is integral WT dV. This is your volume, right? dV. This is equal to constant in time, right? This is what is the definition, right, for you? So implies. So what we have is the ddt. So you take this ddt of integral WT dV equal to 0, right? This is a constant. So I just simply differentiate with respect to time. So this is what happens. So now this implies. So what is that? You see, WT is moving. Okay. So it's moving with time t. So the domain. So right now, if you don't want to, you want it to be fixed. So what do you do? ddt of integral W, and what you will have inside. Once you want to make it fix it, so it should be Jacobian, right? JdV. The Jacobian dV equal to 0. Right? So this implies what? What is the derivative? What happens to the derivative once you inside? This implies what? W dou J by dou T dV equal to 0. So what is the meaning of dou J by dou T? Dou J by dou T we have done now, last class. Dou J by dou T, what is the value? What is that you get? Hello? 10th. Dou J by dou T you have, right? Something which we proved. Dou J by dou T is J into del dot U, right? So that is W, fixed W, J into divergence, del dot U basically you have del dot U, okay? Del dot U at, it's moving. This is moving, right? So this is del dot U, phi of x t, right? Yeah, that's what it is. I mean, once you have a fixed base inside variables are all functions of t moving. Okay, so this is del dot U. U at let's put it like this way. So U at U of x t. So x of t. This is the meaning. Okay. Even here it is the j is also xt. So x comma t. Okay. So this into Jacobian into dv. All moving, right? So that's what it is. So this is also equal to, so this means this is also equal to 0. Now you get back to Wt. So this implies Wt. Now I'm going jdv, I'm putting it, if I put it as dv, so this W is going now moving with time t. So this is actually del dot U dv equal to 0. So do you see the sequence? All of them are 0, isn't it? So if U is if the fluid is incompressible, okay, implies what is that you gain? So Wt is arbitrary, so that will give you del dot U equal to 0. Okay, del dot U equal to 0. And what can you say about J? Hello? So I've given those examples, right? So those definitions of incompressibility means that volume is not changing with time. So that is what is one definition. This is another definition. Now you are getting from your, from the same definition, you are actually deriving. You're seeing that all are equivalent. So what happens to J, the Jacobian J? Also Jacobian will be, what happens? It should be identically 1. Can you see that one? Can you tell why J has to be identically 1? Hello? Suppose it is not 1. Okay? Then what happens? So how do you prove mathematically that J has to be 1? Can someone do this one? J is actually equal to 1. They are all equivalent. Okay? Whatever definitions I gave now, so now incompressible whatever definition, first definition, that is the volume. Volume is constant. Volume of Wt is constant. Basically, that is what you have considered, implies this one. So this also implies this. Is both ways you can go. These are all equivalent. These are all equivalent definitions that we gave. Right? So last class we have seen that incompressibility means see, I have given three definitions, right? Volume is not changing in time. Density, that is extra thing I have given from the equation of mass. Okay. And also equation of mass, or continuity equation or mass equation, you see that del dot U equal to 0. So right now, just by using that integrals, okay, changing those integrals, if you use it, that is exactly what you read, right? So if you use that one, or you have your transport equation. So transport equation d dt of integral Wt f dv. So what do you have here? F is 1, right? So f equal to 1. So dou f by dou t, that is 0, plus divergence of 1 is f, the divergence of u dv. That's how you're getting, no? So basically, how I am getting this one? These are basically our transport equation only, right? Hello? See, this is also true, right? So for every W2, this is true for every Wt, right? Volume. So here, this is also true for every W. This is also true, right? Is a subset of R3. Is a subset of R3, right? So this implies this is 0 and this is also 0, right? So, isn't it? And also this quantity. And if you use, so they are actually, from transportation theorem, these has to be same. They have to be same, right? They have to be same means these things, if this is 0 and j has to be 1. How do you say that j has to be equal to 1? Okay. Hello. This is still question. Okay.
Yes, sir.
Yeah. How do you see that j is actually equal to 1? How j is equal to 1? So if you use your transportation theorem, d dt of Wt dv, okay, that is anyway 0. Left hand side is 0. So transport equation will give you Wt. So if you convert everything, the j is there both sides, right? So is there any other information that you have? Why j equal to 1? Can someone answer? We use just now dou g by dou t. Dou j by dou, what is this one? That dou j by dou t is nothing but this one, right? Now what you got, del dot u equal to 0. So that means dou j by dou t equal to constant. J is constant, right? So this
Yeah.
proof, just to see this one, proof is because del dot u equal to 0, we get dou j by dou t equal to 0. That implies j equal to constant, right? J equal to constant means j equal to j at j is at t and this is at 0. What is j at 0? That is the determinant of the derivatives, right? That is simply, there is no time, right? It is simply same variables. If you do, you will get identity, right? This is simply 1, right? Can you see that? See j of t. Okay, let me put it. This will give you what? This is basically j. J is a function of, what is j? J is both x comma t, right? X comma t. So it's a function of t. So finally, what this will give you, that j of t, x comma t, basically x is fixed anyway. X of t equal to constant, right? How to fix this constant? T equal to 0 you take. So it's a constant. That means jt equal to j0. So what? But j0 equal to simply identity, right? It's 1. Because this is the determinant of dou x by, what do you have? Dou zeta by dou x. What is zeta? If at t equal to 0, that is simply x only, right? Small x, not x bar. X bar is basically x, y, z. So dou x by dou x. Similarly, dou y by dou x, dou y, dou z by dou x. So first row you got. That is exactly you're getting 0, 1, 0, 0, right? Finally, the determinant is basically I, determinant of I. So that is why it is 1. Is it fine? This one, because this del dot u equal to 0, okay? Since dou j by dou t equal to j into divergence, right? That is del dot t, del dot u, right? J into del dot u, right? So this is equal to 0 means what do you have? So from this is true for every w, right? So that means dou j by dou t equal to 0. Okay, that implies jt equal to j0. J0 is 1. So that means finally j is nothing but simply identically equal to 1. Did you get it? So for incompressible fluid, so all these three statements are equivalent. So what are those? A fluid is incompressible, whatever definition you give, the volume. Okay, so volume of Wt equal to constant. The second one, del dot u equal to 0. The third one, what is the definition that you give? That anyway coming from equation of mass, the other definition that we give. Okay, density, basically the density is actually moving with time. Density is not changing. That means capital D rho by dou t. That's what you have written, right? So that is anyway coming from once you use del dot u equal to 0. So that is exactly what you get from your equation of mass. Okay, that we'll see. So this tells you that whatever you have done just now, this tells you that these statements are all equivalent, identically equal to 1. So now this is also equivalent to another equivalent. So these are 1 implies 2. Okay, so 2 implies both sides. This one, and this 2 is also implies d rho by dou t, dt equal to 0. This is using mass equation. Can you see all this? Any question up to here?
No, sir.
You start with here. This is what you get. Okay, this is same as this is you simply take the derivative both sides 0. Then you convert this into change of variable, and then you have now this is nothing but because the w is fixed, d dt once it go inside dou j by dou t. Now we know that dou j by dou t equal to j into del dot u. That is what we put, equal to 0. This is true for every w. Implies this is 0 and this is 0. Dou j by dou t is 0. Okay, dou j by dou t is 0. So this you convert back to wt, del dot u is equal to 0. So wt, this is also true for every wt. So implies del dot u is equivalent to 0. Similarly, dou g by dou t equal to 0 means basically j of jt is nothing but j of t is nothing but 1. The Jacobian is identically equal to 1. So these two are all are equivalent. Okay. So along with that, we also gave another definition of incompressibility using the mass equation. Total derivative, material derivative is of the density is also 0. These are all 4 equivalent definitions for incompressible fluid. Okay. So rho is basically, we have seen that rho is depending on capital X of t and t, right? So you say that if it doesn't vary with space, suppose rho specifically, okay, specifically if a rho of xt and t, okay, so this is what you have. So this is equal to only function of t. Then what will happen? Simply this mass equation will give you, okay, what will give you? What is the equivalent definition? So here del dot u equal to 0 means here d capital D rho by capital dt equal to 0. Mass, right? Material derivative is 0. Here, what is that? That is equivalent to dou rho by dou. Okay. So this is called homogeneous for homogeneous fluids. For homogeneous fluids, this is the case. Inhomogeneous, right? Incompressible, homogeneous. For example, if it depends, the density is only varying with time, then still it is also true. So here also, so for incompressible flows, equivalent definition is dou rho by dou t. Okay. So basically, the incompressibility, if and only if these are all equivalent. Okay. So what do I do? So the incompressibility implies incompressibility. So all those four definitions, incompressible, if and only if dou rho by dou t equal to 0. Okay. This is incompressibility. This is what you are taking, capital D rho by dou dt equal to 0. So because if you consider this rho only depending on time, that is nothing but simply dou rho by dou t, partial derivative of rho. So basically, that's how it is. Okay. Or d, that's what you mean. You write, right? So only depending on time derivative you take. Okay. You can also do you can actually calculate this rho into what shall I say? We can actually solve a continuity equation. Okay. So we can solve the continuity. We can actually solve continuity equation. So what is the continuity equation? How do we solve the continuity equation? In a Lagrangian approach, some kind of Lagrangian approach. Okay. How do we do this one? So we will see how we do this one. So this is actually what we do is you take f equal to 1 in the transportation equation. Okay. Let f of f equal to 1 in the transport equation. Then what is that you get if you do? So if you take this one, what is that you get? Mass conservation becomes mass conservation is basically the continuity equation, no? So what it tells you? Mass conservation transport equation is means what? F into rho, right? Rho, you are involving rho, isn't it? We gave you transportation theorem, right? So rho, if you do, so you have one version of transportation theorem, that is d dt of integral wt rho f dv equal to integral wt rho into df by dt dv. This is one version of transportation theorem. You understand, right? So in this, if you take f equal to 1, basically what you are seeing is one definition of your rho, right? That is a mass. Rho dv means volume changing is incompressibility. Now you are putting inside not just dv. F equal to 1 means you have a rho. Mass is the rate of change of mass is basically what you have right hand side because of F equal to 1, that is 0. It's nothing but your equation of continuity. Okay, so is actually this is equal to transportation theorem. Transportation theorem with F equal to 1. That is this one. Okay, you see this one. So what you have is basically d dt of integral Wt, and put this Wt. Wt, now you have simply rho dv equal to right hand side is anyway 0. Okay, so this is what you want to say. How do you solve this one? So what I write here is basically what it tells you that total derivative is 0 at time t, that is at time t, rho x comma t. Okay, so basically x is x of t. Okay, and this is now we wrote rho x is fixed as though it's fixed because w is moving. Okay, so this dv equal to, it's a constant, no, total derivative is 0. So this should be at time t is same as at w at t equal to 0. W, you call this w t equal to 0 is this one. W0, what will happen here? Rho x is fixed and at t equal to 0 dv. That's what it means, no? This is your mass. Total mass is, rate of change of mass is 0. So initial mass is same as mass at time t. Both are same, right? So now you use the change of variables. Now it will become what will happen here now? Fix it, right? So once you fix it at time equal to 0, so you want to, you do it over, initially w is nothing but your w, no? So earlier when you say fixed volume is, that is initial thing, that is at t equal to 0. So this becomes at if you change this to change of variable the left hand side integral, this becomes simply w naught. W naught is nothing but w only. At w means at t equal to 0, what happens to, what is your wt is nothing but your w. Earlier we wrote. Now we are simply writing as w naught at t just for clarity. So here you have to write rho at x of t, that is x is nothing but your p of xt comma t. Okay. Now it's basically it's moving with time t, rho. Okay. And then here you get a Jacobian of xt dv equal to w naught. What is the right hand side? So you'll have rho of x comma 0 dv. Now w, this is true for every w naught, right? W naught r3, isn't it? This is true for every wt is r3. Any questions up to any questions here? So what is that you have now? That because it's arbitrary, whatever is inside is same as this one, right? So this gives you rho of this function, this xt. So x is varying with time, spatially and temporally varying density function into the Jacobian function. Okay, this Jacobian is equal to the rho at this x comma fixed at t equal to 0. So this is what is mass conservation solution. Okay, is also called mass conservation. Okay, this is also called conservation of mass. So this is the equivalent form of equation of continuity. Okay, this is equivalent to mass conservation. So not that you basically, because the rho is given, okay, initially, see in terms of initial thing for all times. So basically d rho by dt, right? So for incompressible fluids, this is what you have done. Anyway, so incompressibility means d rho by dt, right? the total derivative of that is equivalent, right? This one, this is equal to 0. So we actually calculate what is your rho of x variation with spatial variation with time, and also time variation. So that into Jacobian is actually this one. This is how you get your some kind of you basically solve, you're trying to get in terms of in terms of initial density. Okay, so it's equivalent to mass conservation only. That's the meaning of solving the equation of continuity for incompressible fluids. Okay, so this is kind of solving means that we can solve the continuity equation for incompressible fluids. Incompressible fluids. Any question up to here? Is it fine?
Yes, sir.
Okay, so now see that is for so far in the last class. What we did is we have only two equations, right? We have given only two equations so far, but there are 5 unknowns, right? So total 4 equations, but for 5 unknowns, right? Mass equation will give you one. Okay. And where is that the fourth equation? The fifth equation is coming. Mass equation, you have to see it like d for incompressibility, del dot u equal to 0 separately, and d rho by dt is also equal to 0. Separately, you have to take them as two equations. Okay. The reason being, you can have a conservation of energy equation. If you derive, even if you derive, you can get it actually directly from the equation of momentum. Okay, so equation of motion, that is your conservation of momentum equation. Second equation, you can actually derive your conservation of energy. Okay, so for that reason, basically conservation of energy for incompressible fluids and equation of momentum. Okay, so conservation of momentum equation, second equation, both are equivalent. So both we give you same equation, kind of thing. So for that reason, but you have 5 unknowns and you have only 4 equations in there. So your total equations in that sense, so the equations that you solve for incompressible fluids. Okay, so these equations are called Euler equations. Euler equations means basically you're considering ideal fluids. Ideal fluid equations are Euler equations for incompressible fluids. Incompressible. Hello? Sir, good evening, sir. Tell me. Sir, tomorrow you are not taking class, no, sir? I'm taking at 6:30. Tomorrow 6:30, okay, okay, sir. Yeah. So tomorrow 10. Tomorrow also, that I don't take. 10 is free. Okay, fine, sir. We already informed the students. Yeah. Yes, okay. Yes. So these are the Euler equations for incompressible fluid. Means basically, so you consider what are the equations now? Can you tell? So you have for unknowns, right? So you have 5 unknowns. 5 unknowns. What are those? U, V, W, rho. What else? P, right? Yes. Those are all five unknowns. 5 equations. So what are the 5 equations? 5 equations are, one is d. So from your mass equation, d rho by dt equal to 0. Okay, and then mass equation itself you are splitting into 2 equations. That is the idea. Okay, and this is one equation. Other equation is del dot u equal to 0. Okay, so 2 equations already here. So the third equation is your conservation of momentum. So this du by dt equal to minus grad p plus this is rho into that external force. So this is conservation of momentum, second equation. This is actually first equation itself is giving you 2, and these are 3, total 5. Okay, this is one equation, this is another one equation, these are 3 equations. Okay, so total 5 equations. This is how you have to take it. So before this is how you solve these equations. So to say this one, so we are at to show that for incompressible fluids, so the conservation of energy we have to derive. So assuming that for incompressible fluids, that only kinematic energy is the kinetic energy is the only source. Okay, source of energy. So if you assume that your energy is only, so we'll derive this. We'll see. Okay, so how this conservation of energy is, you can derive it from is actually equivalent to this equation. Third, this equation. What is that? Equation of motion or conservation of momentum. So this we need to show. So to show this for incompressible fluids, energy is only by the moment of particles, moment of the fluid particles. That is only by kinematic energy. Kinetic energy is the only source. Okay. Only source for these fluids. Okay. So what is the energy, kinetic energy of the fluid? Kinetic energy of a fluid element, for example, W, if you say. So we'll write this kinetic energy for fluid element W equal to, let's write this as E kinetic. Okay. So which is equal to, so half mv square, right? So v is your velocity vector u. This is like a modulus. U square means u square plus v square w, and that square root of u square plus v square plus w square. That is what it means. Okay, this is your Euclidean norm. A square. You are doing it over dw. I mean over w. So half m is required, right? So this v square is there. M means rho over dv. So this is the total volume integral. This is the mass per unit volume. So together it will give you mass over the full W. So this is your kinetic energy. So this kinetic energy, if you see this one, this is actually rate of change. So what is this conservation of energy tells you? Tells you that d dt of E kinetic. This is the only thing, right? We assume, so sorry, incompressible fluids, this is the only source. Okay. So ddt of this one is equal to, what should be this? This is equal to what? What happens? Rate of change of energy is what? What is the conservation of energy? What are the other? What will happen? So the particles are moving. It has a kinetic energy, and within the fluid, work is done, right? Work is done at the surface of the element, also inside by the external forces. So how the work is done? how the energy is basically change of energy, how it takes place. Basically, you do some kind of work done inside on the surface. On the surface, you do some work, or inside from the surface forces, right? Basically, you have a surface forces, right? You have a W. W is a fluid element. What are the surface forces? Force into the distance, right? What is work? Force into the distance. These are the stresses, surface forces, right? P is simply P. If this is the normal direction, is Pn. This is the force. We have seen already, right? These are the forces. For ideal fluids, these are the forces because only normal stresses are present here. So P and bar is basically your force in that normal direction. Okay, this is the outward normal direction. So but it is acting in the opposite. So N is outward normal, so you'll have here. So you want this to be negative because N is outward normal. It is acting on this W, right? On the surface. This is rho W. On the surface of this fluid element, it is acting those forces. So what happens actually here? Minus sign is because N is outward, and you will have this dou W T on the surface. It has happened. Now, what is that you have? So I'm not writing only forces here. The force acting. What is that? It is actually, so it represents this work done. This force into basically what is force dot product with velocity. What will happen? Let me write. Okay, so if you write this, you will understand. So U is the vector dot product with this your P and cap. Okay, so what is this represent? This is your ds. So this F into U means what? Dx by dt, right? F into dx by dt, right? F into distance, rate of change, the rate of work, right? That's what it means, right? Hello? Please interact so that whether you are following or not, we understand. See, for example, force, what is work done? Work done is force into distance, right? Now, rate of work, rate of change of work is basically ddt of this, right? So this is same as, for example, yeah, anyway, fixed force, you want this to be dtt, distance by time. This is nothing but F into U. That is what you are seeing here. Do you understand?
Yes, sir.
Yes, sir.
This is the rate at which this work is done on the surface. Okay, by the fluid elements, by the fluid. Okay, so if you consider this fluid, basically what is that? What is done is this is the rate of work done by the surface forces. Okay, that is the pressure forces. Rate of work done by the. So I'll just write this. This is nothing but this first one. This first one. If you write this, rate of work done by the surface forces. What are the surface forces that we have? That's a pressure, right? That surface forces means basically surface normal stresses. Those are only pressure for the ideal fluids. That is one. And what are the other sources that is possible? By the gravity, for example, external force. So here also you'll have, now this is the volume integral dt, and here also rho is also there, right? So why rho? Rho b, right? That is your rho b, right? Without u, that is rho b. So here also you have u dot product with rho into b into dv. So this is your 2. So 2 is the workforce. Work 2 is a rate of work done by the external forces. Okay, do you understand? So this rate of work done, and this is the left hand side is the change of rate of change of energy. So this is your 0 if you say. Okay, so or I'll just write it without putting anything. So this is, if you say third, you can, or simply this is rate of change of energy. Rate of change of energy, which is equal to this, that is nothing but the rate of work done by the both the forces that are present in this case. Okay, so there is nothing else in the system. There is no other energy in the system, for example. Okay, so if you have temperature there, that is different. So then you have to consider some internal energy. So you have a kinetic energy only present for the. We are assuming that you have only kinetic energy is present. So that's what happens for the incompressible fluid. Okay. So what is that left hand side? Now you have to write what is in your left hand side. So left hand side is the rate of change of kinetic energy. Let me write it. So if you write it as ddt of what do you have? So you already kinetic energy we know. So this we wrote it as Wt rho into the Euclidean norm of this vector u square dv. Okay, so this is equal to what? Transportation theorem you can apply, right? Now this half anyway comes out. This is your full F, right? This is only scalar quantity, right? By the transportation theorem, this is nothing but half comes out. Now you apply your transportation theorem. This becomes Wt. This is becomes simply rho comes out. Rho into F. This is F is norm u whole square is your F. Okay. Can you see rho into F? Basically, this acts like F. Rho F. Okay. Rho into F. This whole thing is like rho into F. I'm not writing now. So this is your F. So rho into D capital D, that is your material derivative of F. F is here U bar square. Okay. By dt dV by transportation theorem. Where is your transportation theorem? We just now wrote somewhere, right? Same thing. Where is that? Yeah, this is the one we wrote. Yeah, this is exactly what we used. Whatever in this, right? The same thing we used here. So by the transportation theorem. Now, what is this one right hand side? This is equal to, how do you write this one? What is this u mod this norm means what? This square means what? This is basically u dot u only, right? Right?
Yes, sir.
Since this is this, you differentiate twice. Okay. So what is that you get? D dt. So both sides, if you do this one, d norm u bar square divided by capital dt is nothing but 2 times u dot du by dt, isn't it? Is the dot product. The reason is you do it, dot product both a dot b is same as b dot a, right? So that becomes both are same, so they have 2 times. That 2 cancels, so what you get is Wt rho into. Now what I am writing is that u bar. So rho is a scalar, so now you have a vector u dot product with, so that du by dt, so you can write like dou u by dou t plus u dot gradient acting into u. Okay, these are all vectors. Okay, so this whole thing is one. The dot product is the vector. So now this is your dv. That is what is your right hand side. I mean left hand side. Whatever in your conservation law. The right hand side, you have to see what it happened. So Okay, this is equal to, now the left hand side is this one, right? That's your left hand side. So let me write it as a left hand side. This is your LHS. LHS of conservation of energy. Equal to this. Now the right hand side of conservation of energy, you see. Energy conservation. So what is that you have? Now if you look at this right hand side, equal to, yeah, can you see now what is that you have? So you already have now, so that you can put it in terms of WT. What is the right hand side? Minus dou WT, right? U dot P. So how do you write it? P into U bar, right? P into U bar dot N cap ds. That you use your, what is that you use? Divergence theorem, right?
Yes, sir.
So if you apply divergence theorem there, so what you get is minus, say minus comes out. So this is WT, and you have a del dot, that PU. P is a scalar, U is the vector. So this is the dot product you get, or dV. Now what is the other thing that you have? That is going to be plus, there is already WT is there. What is that? There you have. There what you, as it is, I think you have to write, like rho U, right? That is rho U dot B. Or both are same. U bar dot rho B, all are same. Okay. So simply write rho U, whichever way you like. So rho U dot B, or external thing. This is our dV. Now both sides you have a WT, right? So this is true for every WT subset of R3. So now this is equal to this plus this, right? This minus of this. So implies, now I am writing directly. Okay, now you apply your dot product. Okay, now use your compressibility, incompressibility. So if you use incompressibility, what will happen here? Where is your incompressibility now? Incompressibility, how do you use this one now? Okay, maybe here you may have to use the incompressibility. So this is equal to minus WT. This is what? Del P dot U, right? So our U bar dot gradient of P plus P into del dot U equal. The del dot U is 0, right? Plus P into del dot U. This is equal to 0 by incompressibility. And this is become minus. This time I take the minus for both of them. Okay. So this minus, this also if you include, so this is simply rho U bar dot B bar dV. Okay. So what you have is minus WT U bar dot grad P minus rho U dot B bar dV. Okay. And the left hand side is left hand side equal to right hand side I'm writing. Okay. So that is your yeah, this is your right hand side. So now you can put it together. If you want another sentence, if you say that WT rho into rho is there, right? Rho into U bar dot this is your dou U bar by dou T plus U bar dot grad U bar U dot grad acting on U bar. Okay, so that's what we wrote here. So this one, finally dot product, right? So that is same as this only. This one. Hello, are you there?
Yes, sir.
What is that sound? Someone just left. Oh, wants to join. Who is this? Someone wants to join. Who wants to join? Anyway. So okay. So this is equal to, so this is your dV equal to, on the right hand side you have Wt U dot grad P minus rho U dot P dV. Yeah, what you can conclude? This is the equation of continuity. Okay, so this is the equation of, this is true for every Wt subset of R3. That implies this is equal to this one, right? So this implies rho into, I'm going to leave soon, okay, don't worry. So this is your U bar dot dou U by dou T plus U bar dot del U, okay, equal to minus U bar dot del P minus minus plus. Okay, so if you want this minus this, okay, so that's, you make it plus, okay, don't have to write like that. So that's minus minus plus, here rho U bar dot D bar, right? So this you can get it directly from your from how do you get this? This is equivalent to conservation of momentum. This is basically you make a dot product with U, exactly, right? So how you get this one? So this is nothing but you are basically U bar dot product with rho into du by dt, isn't it? That's what it is now, equal to minus or U bar dot minus grad P plus rho B. So you remove, this is true for every U bar, right? So this is what is the conservation of loss, right? This is the equation of, energy conservation, right? Energy conservation. How you get this? This is actually you get it from only your conservation of momentum, right? So this is basically you take the conservation. This you, how did you get this one? This is simply U dot product with conservation of momentum equation. Okay, equal to 0 implies equation of energy conservation, isn't it? You multiply with velocity vector dot, take a dot product. That's what is exactly your equation of above equation, right? So they are actually equivalent, right? So you take the conservation of momentum. Momentum, I should write clearly. Conservation of momentum, you take make a dot product. That is what exactly equation of energy. So you are not gaining anything. Okay, so that's how they are equivalent. Fine.
Yes, sir.
Or you simply take, so if you say you take the equation of energy, that is what you hear, to remove that U bar. So that's what that means. That is also, that is exactly, so both are equivalent. Okay, so this is how that's the reason for incompressible fluids. You have only conservation of energy will not affect. So whatever, even if you derive it for incompressible fluids, basically what you are getting is only that is equivalent to conservation of momentum. So, but the question comes now, but you have only 4 equations for 5 unknowns. So for that reason, the fifth, another equation is basically, you don't take that, this is the definition of your incompressibility, second equation. The first equation is actually dou rho by dou t from mass, equation of mass. Okay. Once del dot u equal to 0, that equation of mass will give you d rho by dt. So the extra what is the extra equation here for you? For the definition of your, this is the extra equation. Okay. The one that I'm making now, the tick mark. That del dot u equal to 0 is actually your extra equation. That is coming from your definition of incompressibility. Okay. This is how you do. So if your fluid has the boundary, obviously you will have to give, okay, so some boundary conditions if you want to solve these equations. Okay. You understand? Any questions up to here? So one small thing I'll just finish and I'll go. Okay. So there is one more application of okay, small application. So far, if you look at it, all these things, whatever so far we have used only transportation equation. That's how transportation equation is very important. Okay. So another application I'll try to give you, application of Reynolds transportation theorem. Okay. Transportation theorem. So you can actually give a kinetic condition at the surface. You know the surface, right? Interface between the fluids, for example. Okay. So if you give the interface between the two fluids, for example, consider water. Water in the ocean, no? What is that ocean? What is the free surface that you see? Let me write it. So this is like zeta of xt. What is this one? This is equal to 0. Okay. So this is equal to, z is in the direction of upwards. Okay. Depth. So z minus eta. This is the surface elevation of x comma y comma t. It also varies with time t, equal to 0. So this is the surface. This is the free surface. Free surface of the fluid. Just imagine. Okay. Now if you apply your transportation theorem, what is that you gain? What is the theorem tells you? What is the transportation theorem if you apply here? This is your zeta. Zeta is a scalar function, right? Do you see there's no vector here? This is only scalar function, right? Is this a scalar function? Yes, right? Just like rho of x, y, z and t. These are all your scalar function. So if you apply your Reynolds transportation theorem, what is that you get? Okay, just try to apply. Okay, so maybe I'll stop you. So you're not responding. Is it fine? Or shall I complete and go? Or maybe next class I will do. Hello. Next class you want to do? Okay, it's fine. Yeah. Okay. Okay. Yeah. Okay. So we'll see maybe next class. Okay. Yes. Hello.
Yes, sir.
Yeah. Please. Yeah. Okay. Go ahead. Leave. It's enough. So we'll see next class tomorrow. So tomorrow evening we will meet.
Okay, sir.